Hello everyone. Today I will talk about three-dimensional geometry and one of the important chapter of three-dimensional geometry, that is the plane. A plane surface, or simply a plane, is a flat surface, and the flatness of a surface is defined by the fact that the line joining any two points on it lies wholly on the surface. So we can say an important theorem: a plane is represented by a linear equation in xyz, and conversely, any linear equation in xyz represents a plane. So let's verify those. So before we write the equation of a plane, let me give you some idea about some solid geometry. So from solid geometry, it is known that a line is perpendicular to a plane if and only if it is perpendicular to any line lying in the plane. It is also known that if a line is perpendicular to a plane, then all the lines parallel to it are also perpendicular to the plane. Thus, there are infinitely many lines perpendicular to a plane. Any such line is called a normal to the plane. So, how will you define the normal vector? A non-zero vector lying on a normal to a plane is called a normal vector or a perpendicular vector to the plane. So if you consider this is the plane, this is your plane suppose, then this is your normal vector. This is the direction of the vector lying on the normal. So any such perpendicular line, you can take anywhere, because you know vectors are parallelly shifts. We can shift the vectors parallelly. So any such perpendicular line is called the normal vector or perpendicular to the plane. So for writing equation of the plane, normal vector is a very important. So now what initially we talked about, that any first degree equation in xyz represents a plane, that theorem here stated here, and this is the diagram. So you look at that, this is your plane and this n vector is the normal vector to the plane, and the plane passes through a point p naught, right? And any point anywhere on the plane is p. P is a point anywhere on the plane. So let me explain that part. How will you write? This is the vector. Okay. So this p naught, suppose the coordinate of p naught is x naught, y naught, z naught. If you consider, and p is a variable point on the plane, so coordinate of p is, let me first talk about the Cartesian one. I will talk about the vector one also. So coordinate of p is x, y, z. Then the vector p naught p is x minus x naught. I will write the vector components inside the curly brackets. Y minus y naught, z minus z naught. Right? This is your vector p minus p naught. P naught p. You can write p naught p because the direction is, so this is your p naught p. And you look at that, n is a normal vector perpendicular to the plane. And suppose the component of n is a, b, c. This is a vector, so its components written in the curly braces. So you see n and p naught p are perpendicular to each other because n is the normal vector perpendicular to the plane. So it will be perpendicular to any line on the plane, right? And p naught p is such a line or vector. So you have the result n dot p naught p equal to 0, right? And if you take the simple dot product, it will give you a x minus x naught plus b y minus y naught, right, plus c z minus z naught, right? So this is the equal to 0. So this is the Cartesian equations of the plane. So, and if you expand, you will have ax plus by plus cz, and ax naught plus by naught and cz naught, if you take on the right hand side, it will give you a constant, or you can take it as a some scalar d. So ax plus by plus cz plus d equal to 0 is the general equation of the plane, because if you expand this line, you will get this equation. So this is the general equation of a plane. So general equation of a plane is given by ax plus by plus cz plus d equal to 0 and xyz. So any first degree equation in xyz represents a plane. ABC are not simultaneously 0. All the coefficients are not simultaneously 0. Maybe some of the coefficients are 0, but that will represent a plane in 3 dimension. So another one, just already we have proved this one. Equation of a plane passing through the point x naught, y naught, z naught and having normal vector ABC can be written as in this form. Just already we have proved this diagram from this diagram. So this is the equation of a plane passing through the point x naught, y naught, z naught and having ABC as the normal vector. Now let me write the equation of the plane in vector form. If r be the position vector of P and r naught be the position vector of P naught, so P naught P is given by r minus r naught, and if you take the dot product with n, then this will give you the vector equation of a plane. This is the vector equation of a plane. This is the same diagram. You are taking the vector notation, and if you take the components, it will give you the Cartesian form. And if you don't take the component, then it will be in the vector form. So it's very easy to convert your Cartesian form to vector form and vector form to Cartesian form. Next, we'll state a theorem, a necessary and sufficient condition that the equations a1x plus b1y plus c1z plus d1 equal to 0 and a2x plus b2y plus c2z plus d2 equal to 0 may represent the same plane is that the coefficients of the equations are proportional. Okay, so a1 by a2 equal to b1 by b2 equal to c1 by c2. So they will represent the same plane if the coefficients of equations are proportional. Now let us discuss about some special cases of the first degree equation. So you have a plane. Let us consider the plane ax plus by plus cz plus d equal to 0. Suppose one of the coefficients ABC is 0. So let us suppose that for our case c equal to 0. Then the equation takes the form ax plus by plus d equal to 0, right? Because c is 0. So in this case, what is your normal vector to the plane? A, B and 0, because there is no z coefficient, z. So coefficient of z is 0. So AB0 is the normal vector. So its projection on the z axis is 0. Why? Because you see, if you draw the axis, so along z axis, what is your along z axis, what is your direction cosine of the z axis? 0, 0, 1, right? Right? So 0, 0, 1. So if you take the dot product with this vector and this normal vector, it will be 0. That means this plane is perpendicular to the, this normal vector is perpendicular to the z axis. If you consider this normal vector, this is your normal vector AB0, right? So this normal vector is perpendicular to the z axis. Your upper one is the z axis, this is your x axis, this is your y axis, right? So you see your perpendicular, normal vector is perpendicular to the z axis. That means the plane passes through parallel to z axis or passes through the z axis according as d not equal to 0 or d equal to 0. Okay, so you can consider c, in this case we have considered c equal to 0. So we can consider b equal to 0. Suppose we are considering b equal to 0. If we consider b equal to 0, then if it is b equal to 0, then ax plus cz plus d equal to 0, right? In this case, what is your normal vector? a0c. So what is the direction cosine or direction vector of the y-axis? 0, 1, 0, right? So that means this vector is perpendicular to the, if you take the dot product, that will give you 0 only. So that means this normal vector is perpendicular to the y-axis. If you take y this way, this is your x, this is your y, this is your z. So this will be, this is your normal vector, right? a0c. So this will be perpendicular to y-axis. Or you can say the plane is parallel to y-axis or passes through the y-axis according as d not equal to 0 or d equal to 0. Same conclusion. And if you consider a equal to 0, you can find the plane will be parallel to x-axis or passes through the x-axis. Okay. So these are the cases. So similar conclusion can be made. So this is the case if one of the coefficients is 0. That means the easiest way to identify is that the missing variable. You look at that, your missing variable is z. That means this represents the plane in 3 dimension parallel to z-axis or passes through the z-axis is d equal to 0. If d equal to 0, it will pass through the z-axis. Otherwise, it will be parallel to the z-axis. So look at the missing variable always. Let's come to the next case. If two of the coefficients are 0, so b equal to 0, c equal to 0, then your equation takes the form ax plus d equal to 0 in 3 dimension. But in 1 dimension, it will represent a point. And 2 dimension, it will represent a straight line parallel to the y-axis. But in 3 dimension, it will represent a plane. In this case, the normal vector will be a0, 0. So your missing variables are yz. So without any calculation, you can conclude that this will represent the plane parallel to yz plane, right? So if you draw again the coordinate axis like this, this is your x, this is your y, this is your z direction. So this is your xy plane. This is your xy plane, right? That means the floor of your room or floor where we actually keeping our foot. So that is your xy plane. This, and one of the wall is your xz plane. This is your xz plane, right? And this is your yz plane, right? This is your yz plane. Okay, clear? Xy, yz. So if two of the constants are 0, that means ax plus d. So your missing variable is yz, and your normal vector to the plane is a0, 0. So naturally it will be parallel to the yz axis, or you can say yz plane. It will parallel to the yz plane. So this is your yz plane, and this new plane will be look like this. This is your plane. This is like yz plane, parallel to yz plane. This blue marked area or plane is the plane parallel to yz plane. It's just like a wall. It's another wall. You are putting an artificial wall after the yz plane. So that will represent the yz plane. And coincide with yz plane if d equal to 0. So that is the case. So if suppose a equal to 0, c equal to 0, so that will be your by plus d equal to 0, right? And that will represent the xz parallel to xz plane or passes through xz plane if d equal to 0, right? So similarly, you can explain about cz plus d, that is parallel to xy plane, right? Because your missing variables are x and y. So similarly, you can conclude about the normal vector and about the planes parallel. So I have explained about if one of the coefficient is 0, if two of the coefficients are 0. Okay. Next, if none of the coefficients are 0, then it will represent the intercept form of the plane. It will represent intercept form of the plane. That means it will represent like this. Yeah, it will like this. It will cut the x-axis at a point a1 0 0, cut the y-axis at b1 0 0, and cut the z-axis at z1 0 c1 0 0. Sorry, cut the x-axis at a1 0 0, cut the y-axis at 0 b1 0, and cut the z-axis at 0 0 c1. So you can write that equation in this form. Look at the form, and where a1 is given by minus d by a, b1 is given by minus. This is the two-dimensional concept. Just you are generalizing the concept in 3 dimension. So look at the diagram here. This will the plane, and it will cut the x-axis at a0 0 actually from this diagram, and this point is actually 0 b0, right? And this is your 0 0 c, right? This is your 0 0 c. So these are the points, and this is the intercept form. So if one of the coefficient is 0, it will represent the plane parallel to fixed planes, and if two of the coefficients are 0, then it will represent the yz plane parallel to yz plane or zx plane or xy plane, depends on the missing variables. But if none of the coefficients is 0, it will represent the intercept form of the plane. Let us summarize the thing. So you see it is summarized in few points to remember here. Number 1, it represents the parallel to the z-axis. Number 2, it represents the passing through the z-axis plane. Ax plus d equal to 0 represents the plane parallel to yz plane, and x equal to 0 represents the yz plane, y equal to 0 represents the zx plane, and z equal to 0 represents the xy plane. So these are the main concept what we have discussed. Now let me talk about how to find out the equation of a plane passing through 3 points. If the 3 points are x1 y1 z1, x2 y2 z2, and x3 y3 z3, then how to find out the equation of the plane? The equation of any plane through x1 y1 z1 can be written as a into x minus x1 plus b into y minus y1 plus c into z minus z1 equal to 0. And that is already we have learned from the first equation. We have discussed about the diagram, and this is the equation of the plane passing through any point, and ABC are the normal vector. And if this plane passes through x2 y2 z2 and x3 y3 z3, then it will satisfy, and you will get, okay, yeah, it will satisfy. So this will be, yeah, there is some typographical error. So this will be x2 minus x1, y2 minus y1, z2 minus z1, and x3 minus x1, because it will satisfy the equation. So I will replace x by x1, x2, y by y2, z by z2, and in the third one, y3 minus y1, z3 minus z1. Excuse me for the typographical error. So eliminating ABC from these 3 equations, you will get the determinant x minus x1, y minus y1 first row, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, and z3 minus z1 equal to 0. So this is the equation of the plane passing through 3 points. If you don't remember, it's very simple. 3 steps required to find out the equation of the plane passing through 3 points. Now let us have the vector form. So we can talk about 3 vectors. So these are the points, right? And this is the normal vector. So let me explain. This is the plane, suppose. This is the plane, and you have A point and B non-collinear points, actually 3 non-collinear points, C and B. So the position vectors are known to you. Suppose A vector is the position vector of A, B vector is the position vector of B, and suppose C vector is the position vector of C. Now the question is, what is the normal vector to the plane? Normal vector is simply if you can connect AC and connect AB, then these two are the vector. You can get the value. You can get the vector AB, that is B minus A, and AC, that is C minus A. And if you take the cross product, that is AB cross AC, then that is the vector perpendicular to the plane, and that will give you the normal vector, right? So AB cross AC is the normal vector to the plane, because you need the normal vector to the plane to write the equation of the plane. So naturally, your equation of the plane will be AP dot AB cross AC. That will be the equation of the plane. Look at that. Your AP, P is any point on the plane, so it will be R minus A, right? Position vector of any point on P on the plane. So R minus A dot AB cross AC, and AB is your B minus A, AC is your C minus A. Look at that, B minus A cross C minus A, and that will give you the box product. Because if you expand, if you do the calculation, you will get this box product: RBC, RAB, RCA, ABC. If you simplify, and this is the vector equation of the plane passing through 3 points. Vector, actually this box product is nothing but your, it will represent, suppose if I write RBC, that means it's a scalar triple product. That means R dot B cross C, that we write in the box product form. This is box product, or we say scalar triple product. Next is, what is the necessary and sufficient condition of parallelism of two different planes? So if we consider two planes, a1x plus b1y plus c1z plus d1 equal to 0, and a2x plus b2y plus c2z plus d2 equal to 0, then this will represent the parallel plane. Suppose this is one of the plane and this is another plane. So if these two planes are parallel, that means their normal vectors are parallel actually. This is the normal vector for n1, this is the normal vector for the first plane, this is the normal vector for the second plane. So look at that, their normal vectors are parallel. And it is the concept of the vectors. Two vectors are parallel if and only if their coefficients are proportional. So same thing is here. Two planes are parallel means their vectors, normal vectors are parallel. So necessary and sufficient condition is that their coefficients are proportional. That means a1 by a2 equal to b1 by b2 equal to c1 by c2, right? So this is the three diagrams actually. This is the number one is the intersecting planes. That means two planes will intersect, and this is the line of intersection. This arrow, both side arrow, will give you the line of intersection. If two planes intersect, a line is formed. That line is called the line of intersection of the planes. And number two is the parallel planes, and this number three is the coincident. Two planes are actually coincides. Next is the perpendicular. If two planes are perpendicular, then what is the necessary and sufficient condition? So look at that. If two planes are perpendicular, if I draw the diagram, yeah, these two planes, suppose this is the normal vector of the first one. You look at the, you just observe the, you just imagine the normal vectors, abstract. So this is your n2 vector. So if you take the dot product of you look at that, if the planes are perpendicular, the vectors, normal vectors are perpendicular. That means their dot product is 0. So if you take the dot product of both the vectors, e1, e2 plus b1, b2 plus c1, c2 equal to 0. So that is the necessary and sufficient condition, right? So look at that, it's a clear picture that n1 dot n2 equal to 0 is the necessary and sufficient condition for two planes to be perpendicular. And that will give you the simple dot product e1, e2 plus b1, b2, because the components of n1 is a1, b1, c1, and components of n2 is a2, b2, c2. So that will give you dot product a1, b1, a2 plus b1, b2 plus c1, c2 equal to 0, right? Next, I will talk about equation of a plane passing through the intersection of two intersecting planes. So if there is a intersecting planes, let me go to that diagram. Yeah, this is the diagram of intersecting planes. So my question is, how many planes can pass through this intersection, this line of containing this line of intersection? Infinite number. So there will be infinite number of planes passing through the intersection of these two planes. So those equations can be written as lambda into the first equation plus mu into the second equation. Lambda into the first equation plus mu into the second equation, and lambda mu are arbitrary parameters, numbers not simultaneously equal to 0. So if you change the values of lambda and mu, you will get different planes. So there are infinite number of planes passes through the intersection of two intersecting planes. Look at that, you have a intersecting planes, and this containing this line of intersection, you will mention in the line of intersection is mentioned here. So containing this line of intersection, there will be infinite number of planes passes through the intersection of these two planes, plane 1 and plane 2. Now I have to find out what is the angle between two intersecting planes, and that is given by cos theta equal to L1 L2. If L1 M1 N1 are the direction cosines, then the cos theta is given by L1 L2 plus M1 M2 plus N1 N2. As the actually angle between two intersecting planes, the angle between the vectors, normal vectors, and that will given by the vector formula, because A1 B1 C1 and A2 B2 C2 are the direction normal vector, not direction cosines. So you have to convert them into the direction cosine. So I am writing L1 L2 plus actual the formula is L1 L2 plus M1 M2 plus N1 N2. This is the direction cosine. If this is not the direction cosine, you have to convert direction cosine into direction vector. So that is the form. If you convert them, this is the form. So cos theta is given by, it's the same thing. The angle between the planes means the angle between the normal vectors. Look at that, the normal vectors at an angle theta. This is the time. N1 and N2 makes an angle theta, and if you know the components, you can write the theta angle between the vectors. This is the diagram. Okay, because this total angle is 90 degree. So this angle is theta, this is 90 minus theta, this is simply theta. And what is the distance of a point from the plane? So you have a point P, x1, y1, z1, and this is the plane. And what is the distance? This is the distance of the point from this plane. This plane is given by ax plus by plus cz plus d. It's a generalization of the two-dimensional concept. If the point is your x1, y1, z1, then your perpendicular distance is given by ax1 plus by1 plus cz1 plus d modulus, definitely root over by over root over a square plus b square plus c square. It's just the simple two-dimensional generalization of two-dimensional concept. And what is the normal form of the equation of the plane? You maybe remember about the normal form of the straight line in 2 dimension. So in 3 dimension also plane has the normal form. If the plane whose distance from the origin is p and the direction cosine of its normal, actually its direction cosine of its normal vector are given by, if the normal vector of the plane makes an angle alpha with the x-axis, beta with the y-axis, and gamma with the z-axis, then its direction cosine of the normal vector is given by cos alpha, cos beta, cos gamma. Then this is called the and p is the distance from the origin of the plane. If this is the plane, its distance from the, look at that, the red line is the distance of the plane from the origin, and that is given by p. Then its normal form can be, it can be shown that its normal form will be x cos alpha plus y cos beta plus z cos gamma minus p equal to 0. So this is the normal form of the plane. And what is the sine distance? It is stated in the theorem. If the normal form, if you know the normal form, then the sine distance of a point x1, y1, z1 is given by, if you substitute the point in the plane, equation of the plane. So this is the sine distance, x1 cos alpha plus y1 cos beta plus z1 cos gamma minus p. So this is the sine distance of the point from the plane. So that's all for today. So specially we talked about plane, and obviously I will, in the next video I will discuss about the straight lines. So plane, we'll discuss about plane once again, because straight lines and plane are two fundamental and most important platforms of the three-dimensional geometry. Without that, you can't build up any geometrical three-dimensional figure. So you have to learn plane and straight line. Thank you, all of you.